Hi, I'm Kevin Buzzard and this is the solutions to sheet 2 of section 6 of my Formalising Mathematics 2022 course. And in this sheet I talk a lot more about quotients. For example, I show that once we've made this setoid thing, I don't know why they got setoid, sounds so crazy. This thing S, which is a pair consisting of a binary relation and a proof that it's an equivalence relation. Once we feed it into the type class inference system by making it an instance, then all of a sudden we have these two pieces of notation. We have this thing that looks like an equivalence class. In some sense it is an equivalence class. So that's the equivalence class of n in Z mod 37, and we have a notation for the equivalence relation R. So that's kind of nice, and I show, for example, this is the full name of this function. This equivalence class notation is just notation for the function called quotient.mc. The equivalence relation is the same, by definition, the same as R. The proof is REFL, and then I prove various facts. For example, two things are equal in the quotient if and only if they're equivalent. And I show you the names of these things. You see, these are not tactics, right? What's going on here is the exact tactic, right? All we're using is the exact tactic and the REFL tactic. These are not new tactics. These are new. I'm showing you new sort of lemmas that we haven't seen before, that are in Lean's maths library. Actually, I think these ones are probably in Lean's core library. And then I'll talk about well-definedness, and what's going on there is that if I want to define negation on Z mod 37, so we've got Z mod 37, it's the quotient of Z by this equivalence relation. And if I want to define Z mod 37, I'll say take an element in the equivalence, take an element of the quotient. Think of it as an equivalence class. That's like infinitely many integers, all of which are congruent mod 37. Take one of those integers, take its negation and reduce it mod 37. I claim that's the definition of negation on the quotient. Because we're trying to, we've got a negation map from the integers to the integers. We want a negation map from the quotient to the quotient. So I lift to the integers, and then I do negation there, and then I go back down again. And the problem with that is that story is not quite well defined in the following sense. I start off with an element of the quotient, and then I lift it to an integer, and there's a lot of choice there, right? There's infinitely many integers. If I start with 3, there's infinitely many integers congruent to 3 mod 37. So I might lift to 3, but I might also lift to 40, or one of the infinitely many other things. So the definition, as I've explained it, is not sort of well defined, as mathematicians call it. So we have to check well-definedness, and that boils down to checking that if we've got two things in the same equivalence class, then when we minus them, when we negate them and then reduce mod 37, they become equal. So this is the key lemma to prove that negation is well-defined. We've got two integers, and we know they're congruent mod 37, and then I claim if we negate them both and reduce them both mod 37, then these resulting things here are equal. And I guess the first thing to do would be to apply quotient.sound, or rewrite quotient.egg. And the reason we apply quotient.sound is that, you see, when we started off, this is a question about equality. This is equality in Z mod 37. But we don't really have much, we don't know much about Z mod 37 right now. We'd rather be working with the integers, where we have a huge API that we know how to use. There's things like ring and Linarith and a bunch of stuff that works very well. Z mod 37, we're in the process of making it, so not much works at this point. We've only just defined it. So we'll apply quotient.sound. This is the thing that says if things are equivalent, then their reductions are equal. And so now this is just a question about integers. We've got to prove that if A is related to B, then negative A is related to negative B. And now we know how to do this kind of thing, because A is related to B. That's just notation now for R of AB. So this just says there exists an integer such that B minus A is 37 times that integer. So we can do cases H with with X H X. So now we know A minus B is 37X. And now we've got to prove that minus A is equivalent to minus B, and that will, that says, what does that actually? We could, if you like, we could unfold this. Where was that? I mean, let's rewrite equivdef just to see it, and let's rewrite rdef just to see exactly what the question is. So we know that A minus B is 37x, and we've got to prove that minus A minus minus B is 37z. What that minus A minus minus B, that's minus A plus, that's B minus A. And so z is going to be negative x. So let's use negative x. And now, we've seen this situation before, right? So now the idea is we've got to somehow use this hypothesis hx. So we could simp probably left hx. That will probably, there we go. That's done it. Excellent. So the idea is that why did that work? The simplifier changes that into minus 37 times x, and then we substitute hx in by the hx the other way. So that's done that one. And now, as a consequence of proving this lemma, we can now define negation. This says that negation is well defined, and the way that works in Lean is you use this thing called quotient.lift to define the negation function. It's a very unfortunate name. It should really be called quotient.descent, but we're stuck with it. It's called quotient.lift because it's in core Lean, and it means we have negation on the integers. It descends to negation on z mod 37. But to check that everything's well defined, we need this key lemma, and you see that key lemma, the proof of that lemma is being used as an input to this quotient.lift function. Right, and now, and there's a second definition that uses quotient.map instead. So what's going on here is that quotient.map, we could write down a map. We could look lambda a negative a. That's a map from the integers to the integers. And then we want to descend the map from z mod 37 to z mod 37. And if you do it using quotient map instead of quotient.lift, you get a slightly different goal. So this is just sort of a warning. If you start using quotient.map instead of quotient.lift, this goal looks terrifying, right? This goal should somehow say negation on the integers descends to negation on z mod 37. So it should say something like, if we've got some integers which are congruent mod 37, then their negatives are also congruent mod 37. But this goal, I mean, it looks completely terrifying. We could attempt to start unfolding it. In fact, let me show you how that works. We've got this crazy arrow. Okay, so that arrow is relator.lift fun. If we really want to do this in some pedantic way, so we could start by unfolding relator.lift fun. Oh, there we go, that's done it. And now we can see what it says. It actually says if A and B are integers, then A is related to B implies negative A is related to negative B. But if you're sort of brave and you're convinced that that's what this thing says, you could just do intros A and B, right? And that should probably work anyway, yeah, and then H. H says A is related to B, so I'll do rintros, and I'll do C, whatever, Z, H, Z, there. And now we've got lambdas. The way to get rid of lambdas is dsimp only. There we go. And now we've got to see that negative A is related to negative. Oh, so this is just the same. This is just the same goal. We've done this already. The same proof will work here. This is the key thing. If I'd called it x and hx, there, then we use negative x. So it's the same goal. We're defining the same function, so it's not surprising. It's not surprising that it's the same goal. And so that's two ways of defining negation on z mod 37. One using quotient.lift and the other one using quotient.map. But as you can see, they both satisfy this key thing. Negation of the quotient is quotient of the negation. The proof is REFL, which is quite surprising. But that's somehow something that's built into Lean's quotient. And furthermore, the two definitions of negation we've defined are also definitionally equal. Because if you look at the definition of quotient.map in Lean, it'll just boil down to quotient.neg. It boils down to quot.map, which boils down. The definition of quotient.map boils down to quot.lift, and the definition of quotient.lift will probably also boil down to quot.lift. Indeed, it does. Yeah. So, unsurprisingly, these things are equal by definition, right? I think I've said quite enough, so I shall stop there.